Good afternoon to all my AP Chem students. I hope this finds you doing well. This is one of the podcasts that we're going to use for Chapter 13 on equilibrium. And we're going to mainly talk today about LeChateliers Principle. And if you are a chemical engineer and you're in charge of producing some sort of product, LeChateliers Principle is something that you would really be putting into action because you want to maximize the amount of product that you can produce, but you also want to do it in a timely manner. And LeChateliers Principle is something that you'd have to take a look at. So if we say, if you can see, it says if a change is imposed upon a system at equilibrium, the position of the equilibrium will shift in the direction that tends to reduce the change. Now, when I start talking about LeChateliers principle, you're going to think that it seems pretty logical, and it is. It's a pretty simple principle that works, which is always nice. So again, we are talking about the position of the equilibrium. So if I have an effect of change on concentration, the first thing that you need to know is that there is not going to be any change on my equilibrium constant. Now there's going to be a change on the position, but there's not going to be any change in my K. So if I take a look, and if I have a product or a reactant that's added to a system at equilibrium, the reaction will shift away from the material added. So if I have a reactant or a product that is added at equilibrium, the reaction is going to shift away from the material added. So if you think about this, if I add some more reactant, the equilibrium is going to shift right. It's going to shift away from it, which should make sense to you. The equilibrium position is going to move away from it so that it can reestablish the equilibrium and build up some more product. And on the other side is that, so this is, we are adding something. And so if a product or reactant is removed, so I am decreasing something, the shift is going to be toward the material removed. Which also should make sense to you. If you think about a products in your reactants, and if something is going to be removed, they're going to shift toward the direction that the material is removed, which should make sense because you want to reestablish that equilibrium. All right, so if you take a look at page 606 in your book, we are going to take a look at some situations where there's a change in concentration. And you can see that it has an equation there of arsenic, tetra-arsenic hexaoxide, and that is going to be a solid. And I have 6 moles of carbon in the gaseous phase, and this is at equilibrium. I have my arsenic, AS there, in the gaseous phase, plus 6 moles of carbon monoxide in the gaseous phase. So the first thing that it wants to say is that it's at equilibrium and I'm going to add carbon monoxide. So if I go ahead and I'm going to add some carbon monoxide, so this is increased over here, which way is the shift going to go? Well, it's going to shift to the left. LeChateliers principle says that if I add some more reactant, it needs to shift in this direction to reestablish equilibrium. Part B says the addition or removal of carbon or the tetra-arsenic hexaoxide. So we're talking about the reactants. So if I add or remove this material right here, it's not going to matter. It is a solid. You need to recall that that's not in our equilibrium expression, so there's not going to be any effect to this. And then the removal, part C says removal of gaseous arsenic down here. If I'm going to remove this, this is going to be decreasing. My shift is going to continue to go to the right so that I can increase this yield to get back to equilibrium. So that's the first thing in LeChateliers principle. Then the second thing in LeChateliers principle talks about the effect of change in pressure. So if we talk about this, we can, again, if I have effective change in pressure, there's not going to be any change in K. Now there's going to be a change in my equilibrium expression, but there's not going to be any change in my equilibrium constant. So in the same way that I just talked about, If I add or remove a gaseous reactant or product, the same result happens in step 1 when I talked about concentration. It's going to shift away from the added material. If it's removed, it's going to shift in that direction. Another thing that they like to talk about here in pressure is that if I add an inert gas, now again, remember an inert gas is our noble gases. Well, there's not going to be any effect on concentration because this does not have any interaction with anything that's in the equation. Now, the new thing that we need to talk about here is if we have a change in volume of our container. You should recognize by Boyle's law that if I have a change in my volume of my container, Boyle's law says that I have pressure 1, volume 1 equals pressure 2, volume 2. And so what this is saying is that we are taking a look at if I'm going to shift my volume, how is that going to apply to LeChateliers principle? Well, again, we need to recall that volume and the number of moles are proportional to each other with Boyle's law. So if I decrease my volume in the system, the equilibrium is going to shift in the direction of the least number of molecules. So it's going to shift in the direction of the lowest number of molecules. So again, we're taking a look at the number of moles in our situation. We'll look at an example in just a second. So if I increase my volume, it is going to shift in the direction that increases the number of molecules. So it's exact opposite. So now I want you to take a look at page 608. And if you look at 608, you can see that there's an example there where they are changing the pressure, and they have the equation there of they have P4, so with a phosphorus in the solid state. You recognize that that's how that naturally exists. I have 6 moles of diatomic chlorine gas, and this is at equilibrium, and I have 4 moles of phosphorus tetrachloride, and this is in the liquid phase. So the first thing that it wants to do is it says the preparation of liquid phosphorus trichloride by the reaction. And it wants us to know if the volume is going to be reduced, what's this going to do? So part A says the volume is going to be reduced. So the first thing I need to take a look at is I want to take a look at the number of molecules that I have on both sides of my equation. Well, the first thing, if I take a look at my left-hand side of the equation, I really only have 6 moles on the left because the solid is not represented in my equilibrium expression. And then over here, I have a liquid, which is also not included in my equilibrium expression. So I have 6 molecules on the left. I do not have any in the right. So that means this is going to shift right. If I lower the volume, it's still going to shift right. For equation number 2, they have phosphorus tetrachloride in the gaseous phase, 1 mole of chlorine gas in the gaseous phase, and 1 mole of phosphorus pentachloride, and that is also in the gaseous phase. So again, we are going to be decreasing our volume. So let's take a look at the number of moles. I have 2 moles in the gaseous phase on the left. I have 1 mole on the gaseous phase on the right. So 2 to 1 in terms of the number of moles. I have more on the left-hand side, so this is going to shift to the right to reestablish equilibrium if I decrease the volume. And then the last equation that they have there, they have, again, phosphorus tetrachloride in the gaseous phase, trichloride, sorry, and 3 moles of ammonia in the gaseous phase at equilibrium. And this is also in the gaseous phase, plus hydrochloric gas. All right, so we are reducing our volume again. And if I take a look, I have 3 plus 1 in the gaseous phase, so I have 4 molecules here. I have 1 mole plus 3, I have 4 molecules here. It doesn't matter if I reduce my volume because the number of moles are the same on both sides. This will not have a shift in equilibrium. Okay, and then the last thing in LeChateliers principle, let's see, it was back here, is the effect of change in temperature. Well, we should know by now that gases are greatly affected by temperature. And so there is going to be a change in K. So if I have a change in temperature, there is going to be a change in my equilibrium constant due to the temperature effects. So here we have to take a look into an endothermic and exothermic reaction. You should remember that if I have an endothermic reaction, it has a negative sign in front of it, and the heat is taken into the system. So what we have here is we have my reactants, we have plus my heat, and here I'm getting my products. So what's going to happen here if I increase my temperature? If I increase my temperature, there's going to be more heat taken into the system, and so my equilibrium is going to have to shift right. And this is for an endothermic reaction. Oh, I said that wrong, you guys. An endothermic has a positive charge right here. Hopefully you caught that. So it's an endothermic reaction. The heat is taken in on the reactant side of my equation. If I increase the temperature, I am increasing my value of K, and my shift is going to be right. So my equilibrium shift is going to go to the right. Now, if I go ahead and I take a look at, let's get another clear page, part B, if I say I have an exothermic reaction, yes, this time I am on the ball here. It is a negative sign in front of it. So if I have an exothermic reaction, I have my reactants reaching equilibrium with my products, and my heat is going to be released in this situation. And so here, my K is going to decrease as my temperature is increasing, and what's going to happen here is my equilibrium is going to shift to the left. It's going to shift away from this exothermic energy being released. So now if you take a look at page 610, on page 610 it also has an example of LeChateliers, and it talks about the temperature being increased and how that affects the values. So it says, for each of the following reactions, predict how the value of K changes as the temperature is increased. All right, so if I take a look at equation A, I have nitrogen gas, diatomic, oxygen gas. I have 1 mole of both of those, and I get 2 moles of nitrogen monoxide in the gaseous phase, and it tells us that my change in heat is 181 kilojoules. Well, here I recognize, because my change in heat is positive, that that's going to be endothermic. So if it's endothermic, my equilibrium shift is going to be to the right, and my K is going to increase. And part B, it tells us that I have 2 moles of sulfur dioxide gas plus 1 mole of oxygen gas, and this is at equilibrium, and I have 2 moles of sulfur trioxide, and here you should recognize that it gives us my change in heat as 198 kilojoules with the negative sign out in front, so that means that it's an exothermic reaction, and so here my equilibrium shift is going to be to the left because it's exothermic, and so my K is going to decrease. So that's what LeChateliers principle talks about, is very, very simple things that relays what there's going to be a change in concentration, a change in pressure, or a change in temperature. And basically the rules about which direction, if it's added or removed, think about logically what has to happen to reestablish equilibrium. And we will have some more examples of this in class. Have a wonderful day.